Learn like a pro.
When it comes to science and engineering, precision is, well, it's everything. If we want to build things, discover new things, or just understand the universe, we absolutely need a common language. And I'm not talking about English or Spanish. I'm talking about a universal language of measurement. So today, we're going to deconstruct the blueprint for that language, the framework that lets us describe reality with total, undeniable clarity.
So picture this. Before the late 1700s, measurement was just chaos, a total mess. Every little region had its own system. It was a nightmare for science, for trade, for just about everything. The solution? A standardized global system, a universal vocabulary that makes sure a measurement taken in Tokyo means the exact same thing as one taken in Toronto.
So let's really dig into this blueprint for reality. We're talking about the bedrock of it all, the Système International d'Unité, or as we all know it, the SI system. And you gotta understand, this isn't just a dusty old set of rules. It's the universal operating system for all of modern science.
Okay, so what are we actually measuring? We call them physical quantities. And every single physical quantity has to have two parts. It's non-negotiable. If I just say the word 7 to you, it means nothing, right? It's just random data. But if I say 7 meters, suddenly you have real information. You've got the magnitude, that's the number, and the unit, that's the standard we're comparing it to.
This image here really shows that perfect balance you need. On one side, you have the magnitude, the how much. On the other, the unit, the of what. You need both. Without them working together, any measurement just falls apart into useless noise.
So how is a system this powerful actually constructed? Well, it all starts with the absolute fundamentals. The entire SI system is built on just a few core, indivisible pillars. We call these the base quantities.
The best way to think about these is like the atoms of measurement. These are things like mass, length, and time. You can't define them in terms of anything simpler. They just are. They're the standalone pillars holding up everything else we measure.
And here's the crucial part. Each of these fundamental quantities has one and only one universally agreed upon SI unit. Mass is always measured in kilograms. Length, always in meters. Time, always in seconds. This table right here, this is the official language for these core ideas. Now, starting with these fundamental pillars, we can begin to construct more complex ideas. If our base quantities are the atoms of measurement, then combining them gives us the molecules. And we call these derived quantities.
So how do we build these molecules of measurement? It's actually just simple multiplication and division. You take a length and divide it by a time. Boom, you get speed, measured in meters per second. You multiply length by width by height, and you derive volume in meters cubed. Every complex measurement you can think of is built from these simple foundational blocks. And this difference is absolutely critical, especially when it comes to getting accurate results. See, base quantities are what you measure directly in a lab. They're your raw data. Derived quantities, things like speed or density, are what you calculate from those base measurements. And that means any little error in measuring a base quantity will get magnified in your final derived results. One is the source of truth, the other is a calculation based on that truth.
All right, so we have our vocabulary now, the base and derived units, but what about scale? How do we talk about the distance to a galaxy or the width of a virus without drowning in a sea of zeros? For that, we need the grammar of scale.
I mean, seriously, trying to write out a number like 25 million meters is just asking for trouble. It's inefficient, and it's so easy to make a mistake. This cognitive overload is a direct threat to precision. Prefixes are the elegant solution. 25 million meters becomes 25 megameters. Clean, simple, and way harder to mess up.
And here's the toolbox for that shorthand. This prefix slider shows us exactly how to modify our base unit. If we move to the left, we make it bigger. Kilo for 1,000, mega for 1,000,000, giga for 1,000,000,000. Move to the right, and we make it smaller. Milli for 1,000th, micro for 1,000,000th, and nano for 1,000,000,000th.
So what if you need to convert from, say, millimeters to kilometers? You don't have to guess. There's a really simple two-step logic. Step 1, always, and I mean always convert back to the base unit first. In this case, that's meters. It's your anchor point. Then from the base unit, you convert to whatever prefix you're aiming for. It's a foolproof method.
Prefixes are fantastic, they're great for everyday communication, but for rigorous scientific work, I'm talking about situations where precision is everything, and there can be absolutely zero ambiguity. We need an even more powerful tool. This is it. This is the ultimate grammar of scale, standard form. It lets us write any number as a times 10 to the power of n, but it has one golden rule, and this is non-negotiable. The number a has to be greater than or equal to 1, but less than 10. That rule ensures that every number can be written in one and only one way.
And converting to standard form is surprisingly easy with this decimal jump method. For a big number, you just jump the decimal point to the left until you land in that golden rule zone, and the number of jumps you made becomes your positive power of 10. For a tiny number, you jump to the right, and the number of jumps becomes your negative power. Simple as that.
Okay, now for the fun part. Let's see how all these pieces, the base units, the derived units, the standard form, all integrate to create a single, perfectly structured measurement.
We've put all the components on the table, we've assembled the entire system, so now let's actually put it to work on a real-world example. And here it is, the thickness of a single sheet of paper. It's 5.2 times 10 to the power of minus 5 meters. This one little measurement, it perfectly ties together every single concept we've just discussed.
Let's break it down. First, we have the magnitude, 5.2. Notice how that perfectly follows our golden rule for standard form. Then we have the scale, 10 to the minus 5, which tells us we're working at a micro level without having to write out a bunch of zeros. And finally, we have the base unit, m for meters, which connects this whole thing back to the universal SI standard for length.
And this brings us right back to our core principle. That number describing the sheet of paper isn't just data anymore, it's verifiable knowledge. And it's only useful because it's built on a shared, logical, and unambiguous framework, a language designed specifically to eliminate confusion and maximize clarity. So this system for describing reality is really one of the great achievements of science and engineering. It's elegant, it's logical, it's universal. But that leaves us with a pretty critical question. If our language for measurement is so precise, then where do the biggest errors in science and engineering actually come from today? Well, the answer doesn't lie in the system itself, but in how we apply it.